So let us start with the electric charges and fields. So to start with, let us see some experimental observations. Okay, so what are those experimental observations? So let's suppose we have two glass rods. So suppose we have these two glass rods, they are rubbed with silk and they are brought closer to each other. So what happens is the two glass rods repel each other. Okay. Then you have two plastic rods, you rub them with cat's fur, you bring them close to each other, again they will also repel each other. Okay, so two glass rods rubbed with silk cloth, they are brought close to each other. You feel that they will repel each other. Okay, and two plastic rods, they are rubbed with cat's fur. If you bring them close to each other, they will also repel each other, right? Then, if you bring one of these glass rods, which was rubbed with silk, and one of the plastic rods, which was rubbed with cat's fur, close to each other, what will happen? They will attract each other. Okay, so this is one experimental observation. Then, now let's suppose there is a metal ball, okay, metal sphere, and it is hung from some rigid support by means of a nylon thread. Okay, so let's suppose we have a metal ball like this. It is hung to this rigid support by means of a nylon thread. Okay, why nylon? Because it's an insulator. Okay, this is the rigid support and this is metal ball, some metal. Now what you do is you take this glass rod or plastic rod and you bring that glass rod close to the metal ball. Okay, just bring it close to the metal ball and you will see that there is attraction between this glass rod and the metal ball. Okay, so this is glass rod which is rubbed with silk. You bring it close to the metal ball and you will see that there is attraction between the glass rod and the metal ball. Okay, so now what you do is you touch that glass rod with the metal ball. Okay, and again you separate it. You touch it for, you keep it in contact with the metal ball and you separate it. Now what will happen? Again, if you bring the glass rod close to the metal ball, now you will see that it will repel the metal ball. Okay, so what is happening? So now, so people have observed these kind of things for centuries. Okay, and they found some laws. Okay, laws of electrostatics as we call them. So what are those laws? So when you rub two bodies on each other, what happens is they gain some kind of a charge. Okay, some property due to which they attract each other. Okay, so we call that property as an electric charge. So when you rub one body, for an example, when you rub glass rod on silk, so silk gains one kind of charge, glass rod gains another kind of charge. Okay, so first conclusion is when you rub two bodies onto each other, both bodies get charged. Okay, this is first observation. Second observation is when you rub two bodies onto each other, the charges on these two bodies, they are not of same type, they are of different type. Okay, so these charges were called by positive and negative by American physicist Benjamin Franklin. Okay, then what happens is the next observation is there is an attractive force between opposite charges and there is a repulsive force between like charges. Okay, there is repulsive force between like charges. Okay, so we can understand these two experiments, okay, using these conclusions now. Okay, so when you rub glass rod with silk, what happens? Glass rod gains one kind of charge, silk gains another kind of charge. Okay, so basically glass rod gains positive charge, silk gains negative charge. Okay, so silk becomes negatively charged, right, when you rub them. Now, if you bring glass rod close to another glass rod, both were rubbed with silk, so both of them have same kind of charge. That's why they repel each other. But when you bring a glass rod close to silk, then they have opposite kind of charge, so they attract each other, right? So this is simple. Okay. Then same thing happens when you rub plastic rod with cat's fur. Okay. So now cat's fur becomes positively charged. This becomes positively charged, and the plastic rods they gain negative charge. They gain negative charges. Okay. So once again, if you bring two plastic rods close to each other, they will repel each other. And if you bring one of the plastic rod close to cat's fur, so there will be attraction between the two. And if you bring glass rod close to plastic rod, they will also attract each other, right? Because they have opposite kind of charge. So this thing is clear. All right. Now, what happens in next experiment? So next experiment, what you are doing is you are bringing this glass rod close to the metal ball, okay, and you are not rubbing them, right? You are not rubbing them. So what was first observation? When you bring the glass rod close to the metal ball, there is an attraction between the two, okay. So for this, we need to understand what what is matter consisting of. Okay, what does matter consist of? So now we know, we have been studying this since, I don't know, 8th, 9th standard, that everything is made up of atoms. So what is there inside atoms? We know inside atoms there is a positively charged nucleus and there is a negatively charged electron cloud, right? There is negatively charged electron cloud. Okay. So these electrons normally they are connected to, I mean, they revolve in some orbits. Okay, this is the simplistic model, that they revolve around this nucleus. Okay, but in case of metals, so most of the metals they have either one, they are made up of atoms first of all, they are not made up of molecules. Okay, so in their outermost shells, they have either one, two, or three electrons. Okay, and at room temperature, these electrons gain some energy and they move freely inside the metal. Okay, so most of the atoms have electrons detached. Okay, so there are ions which are positively charged and electrons which are negatively charged moving freely inside atoms because electrons are very light. Okay, I said inside atoms, it is inside metals. Okay, so now there are negatively charged electrons moving freely inside this metal ball. Okay, and there are positively charged ions. So when you bring this glass rod close to the metal ball, what happens? So these negatively charged electrons they get attracted by the glass rod, so they gather on this side. Okay, they will gather on this side, right? Ions are heavy, they will stay wherever they are, or there will be a little bit of movement. Okay, so this side will have more of negative charge, the other side will have more of a positive charge, and since this side is closer, okay, this side of metal ball is closer to the glass rod, there will be attraction. Okay, so force between these negative charges and glass rod would be more compared to the repulsive force between this positively charged glass rod and positive side of the metal ball. Okay, but now once you touch once you touch the glass rod with the metal ball, what will happen? These free electrons, now they are attracted by the glass rod. So if you keep them in contact, so electrons will get transferred from the metal ball to the glass rod. This metal ball becomes positively charged, right? The metal ball becomes positively charged. Some of the charge of glass rod will decrease. Okay. So then now metal ball is also positively charged because it is losing some electrons. Glass rod is gaining some electrons, but there was a large positive charge on the glass rod. Okay. So it is not nullified yet. So now when you bring the glass rod and metal ball close to each other, what will happen? There will be a repulsion between them. So is it clear? Some materials, they have tendency to lose electrons. Some materials have tendency to gain electrons. Okay. Some materials have tendency to lose electrons and some materials they have tendency to gain electrons. So this property is known as electron affinity. Okay, attraction towards electrons, you can say, right? So the materials which have greater electron affinity, they will tend to gain electrons. The materials which have lesser electron affinity, they will tend to lose electrons. So this thing will determine, okay, what happens when you rub two bodies onto each other. The body which has more electron affinity will try to gain electrons, and the body which has less electron affinity, it will lose electrons. Okay, now we don't need to remember which bodies have more electron affinity, which of them have less electron affinity, etc., etc. But if you are interested, you can check the table. It's given in our NCERT book. Okay, let us see charging by induction. Okay, so suppose we have a metal ball like this, and it is mounted on an insulating stand. Okay, this is important. It is mounted on an insulating stand. Okay, now what you do is you take a glass rod which is rubbed with silk. Okay, or plastic rod which is rubbed with cat's fur. Anything will do. So let's suppose we have a plastic rod which is rubbed with cat's fur. We bring it here. So this plastic rod has got negative charge, right? It has got negative charge. Is this visible? It has got negative charge. Okay. So now what will happen? The electrons inside this metal ball, they will get repelled, right? Electrons will get repelled and they will gather on this side of the metal ball. Okay. So what charge will be there on the other side? Positive charge, because this side lacks electrons. Okay. Then this side has less number of electrons compared to this side. Okay. Or compared to ions, you can say. So this side has more number of electrons. So that's why there is negative charge. Now what you do is you bring a wire, you connect it to this metal ball. Okay. You connect it to this metal ball, a wire like this, and the other end of the wire you give it to ground. Okay, you connect it to earth. So now what happens is this negative charge or excess negative charge, we can say, from this side, it flows to the earth. Okay, so it goes inside earth. Okay, so earth is a big conductor, right? So this excess negative charge, it will flow to the earth. So now what happens after that? You can remove this wire. Okay, the job of wire is done. Okay, so now you have your metal ball. mounted on this stand, right? So now we have removed electrons, so the metal ball will have positive charge. Okay, so it will have a positive charge. And now you can remove this glass rod also. So these positive charges, they were gathered on this side of the metal ball. Now there will be redistribution of the positive charges so that there is uniform charge distribution on the surface of the metal ball. Okay, so initially there was no charge on the metal ball. Now what happened? You brought this plastic rod, not glass rod. Okay, plastic rod close to the metal ball. So what happened? The charge got induced. Okay, charge got produced. Okay, right? Because of movement of charges inside the metal ball. Okay, so this method of charging, it is known as charging by induction. Now we know that if we have two charges, okay, like or unlike, either they will attract each other or they will repel each other, right? So now the next thing that we want is the nature of the force between charges. Okay, so that was given by Coulomb. Okay, so Coulomb did lot of experiments and he found out the nature of the force between the charges, okay, which we call the electrostatic force. So if we have two charged particles or two charged bodies, okay, like this, and they are separated by some distance, charge on first body is suppose Q1, charge on second body suppose Q2, and the distance between the two bodies is suppose R. Okay, so according to Coulomb, the force of attraction or repulsion between these two bodies is directly proportional to the product of charges of the bodies, okay, and it's inversely proportional to the square of distance between them. So the electrostatic force, this force is known as electrostatic force. So this force is directly proportional to product of charges on two bodies, and it is inversely proportional to the square of distance between them. Okay, and now if you combine this these two, so you get that the force is proportional to what? It is proportional to q1 q2 upon r square. So if you remove this proportionality sign and put an equality sign, you have to put a constant, right? So this constant is determined using experiments, and the value of this constant is 9 multiplied by 10 raised to 9. And what will be its unit? It is, if you take this r square on other side, q1 q2 on other side, so it is Newton meter square per Coulomb square. Okay, so value of this constant is 9 into 10 raised to 9 Newton meter square per Coulomb square if you are measuring this force in vacuum. Okay, so if you are measuring this force in vacuum, right? Okay, so now this constant is written as 1 upon 4 pi epsilon naught. So K is written as 1 divided by 4 pi epsilon naught. This is for convenience. Okay, you might wonder, this constant is K. K is more convenient, right? Pi 1 upon 4 pi epsilon naught. Okay, so we'll see this later. Okay, as we progress through this chapter, you'll understand why 1 divided by 4 pi epsilon naught, 1 upon 4 pi factor. Why is it convenient? Okay, so all right. K is written as 1 over 4 pi epsilon naught, and this epsilon naught is called as permittivity. Of free space. Okay. So permittivity means the permission given by the medium to for the spread of this force, we can say. Okay, it's permission given by this medium for this force to act between charged particles. Okay, that's the permittivity. Now this means that if there is change in medium, what will happen? The permittivity will change. So for some other medium, for any other medium, okay, we'll have some different force. So force is equal to, now we can write it as 1 upon 4 pi epsilon naught multi, sorry, 1 upon 4 pi epsilon q1 q2 divided by r square. So what is different here? So force in some other medium is 1 upon 4 pi epsilon multiplied by q1 q2 divided by r square. So epsilon is equal to epsilon 0 k, small k, and this small k is called as dielectric constant. This is known as dielectric constant of a medium. Okay, so this is just a definition, right? So this is force between two charges. Okay, this is force between two charges. So what is F? F is 1 upon 4 pi epsilon naught multiplied by q1 q2 divided by r square. Now if both charges are positive or both charges are negative, okay, if q1 q2 are positive or negative, both positive both negative, so F will be positive. Okay, and positive means repulsive, right? And if one charge is positive, other one is negative, if q1 is positive, or let's say q1 and q2 have opposite charges, then you will have product of these two negative. So F will be negative, F is negative. So negative means an attractive force. Okay, positive force means repulsive force, negative force means attractive force. Okay, so what will be force if you have multiple charges? So here comes the principle of superposition. So principle of superposition. Okay. So now let's suppose we have n number of charges, q1, q2, q3, q4, q4, so on and so forth, q5, q6, so on and so forth up to qn. Now what will happen? So suppose we want to find out the force acting on first charge. So now the net force on first charge is equal to the vector sum of all the forces acting on first charge. Okay, so the net force is vector sum of all the forces acting on the first charge. So it's just like our mechanical force. Okay, so when you push a body from one direction and from other direction, the net force is vector sum of F1 and F2, right? Just like that. So electrostatic force is not different. So principle of superposition says that net force net force on any charge on q1, suppose it's equal to vector sum of all forces all forces acting on q1 due to all individual charges. Due to individual charges. Okay. So now force between Q1 and, oh, I wrote Q3, right? It's Q2. So force between Q1 and Q2, it will act along this line. Okay. Force between Q1 and Q3 will act along this line. Force between Q1 and Q4 will act along this line, right? So the net force, we can say, let's call it F1 bar, it's equal to, now let's just write K, okay, Q1, Q2 upon R12. What is R12? R12 is distance between Q1 and Q2. Okay. Now we have to consider vector, right? We have to consider force as a vector quantity. Okay. So it will be directed along R12 cap. Sorry, R21 cap. This is force on 1 due to 2. Okay. So this will be the formula. Force on 1 due to 2. So now you draw R21. So let's suppose this is your Q1, this is Q2, and their position vectors. Their position vectors, this is R1 bar, this is R2 bar. Okay. So now the force due to Q2 on Q1 will be directed like this. It will be directed along this line. So this is our R1 bar, this is R2 bar, and this is, suppose, R21 bar. Okay. So it is, what is R21? It is R1 bar minus R2 bar, right? So if you write R1 bar, so R1 bar is equal to what? R2 bar plus R21 bar. Okay. R1 bar is equal to R2 bar plus R21 bar. That means R21 bar is R1 bar minus R2 bar. Okay. So basically what I mean is this vector R21 bar, it's directed from 2 on 1. Sorry, from 2 towards 1. Okay. That's R21 bar, right? So now the direction of force, whether it is attractive or repulsive, it is given by what? It is given by product of charges. Okay, so whether Q2 pushes Q1 or whether it attracts Q1. So see, if both are positive, then what happens? Q2 will push Q1 because this term will be positive. So force will be directed, force by Q2 on Q1, it will be directed like this. Okay, so it is pushing Q1. And if they are oppositely charged, then what will happen? So Q2 will attract Q1. So you will have a negative sign here. Okay. So R21 is directed like this, right? But force will be directed in opposite direction because of the negative sign, right? So force on 1 due to 2, it will have, its formula will be K multiplied by Q1 Q2 upon R12 square, sorry, I didn't write square, multiplied by R21 cap. All right. So similarly, we can write force on Q1 due to Q3. So it will be K Q1 Q3 upon R13 square, and here we'll have R31 cap plus so on and so forth up to plus we have K multiplied by Q1 Qn divided by R1n square multiplied by Rn1 cap. Okay, so net force is just F1 bar plus F2 bar plus so on and so forth up to Fn bar. Okay, so now consider there is a charge. This charge is suppose capital Q, and we have another charge, small q. Okay, so capital Q is big charge, small q is very small charge. Now there is some distance between them. Okay, distance between them is suppose r. So suppose earlier the charge small q was not there at this position. Charge small q was not there at this position, and it is somewhere at infinity at very large distance. You bring in that charge from that position to this position and you keep it there. Now what happens? The moment you keep that charge there, you see that there is repulsive or attractive force between the two charges. Okay, so either the small q will get attracted towards capital Q, and or it will get repelled by the capital Q. Okay, either it gets attracted or it gets repelled. So why did we take small q as very small charge? So that it should not repel or attract capital Q much. The position of capital Q should not change much. Okay, that's why we took it as very small charge. And this one is known as now the test charge. We are considering it to test something. Okay, so now question is, the moment you keep that charge, force appears, right? Force appears. Okay, either it will get attracted or repelled. Now if that charge was not there, then which thing was there? Okay, because once you bring the charge, what happens? It gets attracted or repelled. Okay, once you keep it at that position. But now if you remove it, something must be there, right? Because this charge is at this position. Okay, so what is there at that position when nothing, no other charge, etc. is present? So once there is some charge in some region, okay, in space, it produces its effect in the surrounding region. Okay, it produces its effect in the surrounding region, right? So this effect is known as the electromagnetic, sorry, it is known as the electric field. Okay, this effect is known as the electric field produced by this charge. And how do we measure that effect? So this charge is known as the source charge. How do we measure the effect of this how do we measure the effect of the source charge in the surrounding region? So we bring some other charge, we call it test charge. This is a test charge which is very small, and we keep it at some location and we measure the force between these two charges. So the effect of this charge, which is known as the electric field of this charge, is defined as electric field, or it is also known as electric field intensity. Okay, how strong is the electric field of this charge? Okay, so it is given by force acting on other charge, right? Force acting on test charge. Force exerted by this charge on test charge divided by test charge. Okay, so see what happens if we consider this formula for the electric field. So we get E equals to 1 upon 4 pi epsilon naught multiplied by Q into Q upon R square. This is the force. Okay, divided by what? Test charge. So now when we divide by test charge, Q gets cancelled. What we are left with is E only. Okay, what we are left with is E only. So E is 1 upon 4 pi epsilon naught Q upon R square. So this tells us this effect is directly proportional to what? This charge only, and it is independent of any other charge, right? So it is effect of this charge, electric field, of this charge is effect of this charge in the surrounding region. So it must depend on this charge only. It should be independent of other charges. Okay, so this charge is the source of the electric field. Okay, so the effect of this charge or the electric field of this charge, it is directly proportional to the charge and it's inversely proportional to square of the distance of that location, okay, where we want to measure the electric field, right? So let us see the electric field in vector form. So now let's suppose we have this source charge only and we want to measure its electric field at this point. Let's call the point P. So the electric field of this charge E is equal to 1 upon 4 pi epsilon naught multiplied by Q upon R square, right? This is the magnitude only. We want direction. So this is suppose R and this is suppose vector R bar. Okay, this is vector R bar. Okay, so formula for electric field in vector form will be 1 upon 4 pi epsilon naught Q upon R square. This is magnitude multiplied by R cap, a unit vector in direction of R bar. Okay, now see, if this charge is positive, if this charge is positive, so this is positive, so this field will be directed in this direction, okay, or wherever you take that R bar. So let's suppose you have this charge and this is the point where you want to measure the electric field and this is your R bar, okay. So charge is positive, so electric field will be directed like this. What does this mean is that if you take another positive charge, you keep it at this point, what will happen? It will get repelled by this charge. Okay, it will get repelled by this charge, right? Okay, and if Q is negative, so this is when Q is positive. So if Q is positive, you consider any point anywhere in space, the electric field is directed radially outwards. Okay, what does radially outward mean? Outwards mean from starting from that charge towards the location of the point. Okay, and if you take negative charge, so if Q is negative, Q is negative, then what will happen? So you will have negative sign here. It will be directed in opposite direction of R bar. Okay, so you take some point anywhere, you take this point, let's suppose this is your point P and this is the vector displacement, oh sorry, position vector of the point with respect to Q, okay, and now Q is negative, Q is negative. So the electric field will be directed like this, okay, in opposite direction of R. So now how do we represent this? We represent this using electric field lines. We represent this using a diagram, okay, by means of curves which are known as electric field lines. Okay, so let's suppose we have positive charge like this plus Q and a negative charge minus Q. Okay, so let's suppose we have only positive charge. Now the electric field lines due to this positive charge, they will be directed radially outwards. So these are lines used to show the electric field of this charge. They are known as electric field lines. Okay, so what does this mean? If you keep any positive test charges are always positive, they are small, they are positive. So if you keep any positive test charge anywhere in space, what will be the direction of force acting on that charge? It will be directed along this electric field line. So if you keep a charge here, the force on it will be directed like this. If the charge is negative, it will be directed like this. Okay. So the electric field of this positive charge is radially outwards. Okay, it is radially outwards. And if you have a negative charge, then it's very simple to guess that its electric field will be directed radially inwards, right? So these are electric field lines due to positive charge radially outwards. So electric field of a positive charge is directed radially outwards. Electric field of a negative charge is directed radially inwards. So let's consider this question. 2 point charges A and B having charges plus Q and minus Q respectively are placed at certain distance apart and the force acting between them is F. Okay, so we have this charge plus Q and minus Q, so force between them is F. Okay, now if 25% charge of A is transferred to B, then the force between charges becomes. Now what will happen? This is the question. Okay, so this is plus Q minus Q. This is A and B. Okay, so now when 25% charge from A is transferred to B, okay, so from here to here, so 25% means what? 1/4, right? 25% means 1/4. So 1/4 of charge is transferred. How much charge will be left? 3Q by 4. Okay, and distance between them is same. So this is positive 3Q by 4. Now you are transferring plus 3Q by 4 here. So what will be the charge here? It will be minus Q plus, not 3Q by 4, plus Q by 4, right? So it will be minus 3Q by 4, the charge here, minus 3Q by 4. Okay, so if distance is same, this force F is directly proportional to product of two charges, Q multiplied by minus Q, you can say, and F dash would be proportional to what? 3Q by 4 multiplied by minus 3Q by 4. 3Q upon 4 multiplied by minus 3Q upon 4. Okay, so if you divide these two, then what do you get? F dash upon F will be equal to, so this Q square and Q square, negative sign, it will get cancelled. So it will be just 3Q by 4 square. Okay, so it is 9 by 16. That means F dash is equal to 9F divided by 16. That is option C. Let's see next one. Suppose the charge of a proton and an electron differ slightly. Okay, charge on proton and electron, they differ slightly. One of them is minus E, the other is E plus delta E. If the net electrostatic force and gravitational force between two hydrogen atoms placed at a distance d much greater than atomic size apart is 0, then delta E is of the order of. This is a question that you have two hydrogen atoms. Okay, so hydrogen atom has a proton and an electron, and this is first hydrogen atom. So how much is charge on proton? Given that it is not E, it is E plus delta E. It is E plus delta E. Okay, and okay, so this is one hydrogen atom. So how much would be the net charge on hydrogen atom? E plus delta E minus E. So plus E and minus E gets cancelled. So net charge is delta E. Okay, So you have two such hydrogen atoms. They are placed at a distance d, which is very large compared to the atomic size. Okay. So these are suppose two hydrogen atoms. Charge on this one is delta E, charge on this one is delta E, positive. Then what happens? What happens is the force between them is zero. So there will be some repulsive electrostatic force, and there will be some gravitational force, which is attractive. Okay. So electrostatic force is repulsive, gravitational force is attractive. If they cancel out each other, then the net force will be zero. Right. So how much is electrostatic force? We'll say force due to the electrostatic force is F suffix E, gravitational force is suppose F suffix G in magnitude. One is attractive, one is repulsive. So they will cancel out each other. Okay. So this is K multiplied by Q1, Q2. So which is delta E into delta E divided by R square, and gravitational force is G multiplied by M1, M2 upon R square. So it's given that mass of hydrogen is this much. Okay. So mH square, mass of hydrogen square upon R square. So R square and R square gets cancelled out, and we want to find out delta E. So delta E square is equal to G divided by K multiplied by mass of hydrogen square. Okay. So what is G? The value of G is 6.67 multiplied by 10 raised to minus 11. 6.67. So this is equal to 6.67 into 10 raised to minus 11. Okay, mass of hydrogen is 1.67 multiplied by 10 raised to minus 27. So we just want order of magnitude. Okay, this is 10 raised to minus 27, and we have square of that. Divided by K is 9 multiplied by 10 raised to 9. Right? So let's find out the order of magnitude. So this is of the order of 10. Okay, this is of the order of 10. 10 multiplied by 10 raised to minus 11 is 10 raised to minus 10. Okay, and this is also what? 10 raised to plus 10. If we take it in numerator, it will become 10 raised to minus 10. Okay, so delta E square we have 10 raised to minus 10 square multiplied by 10 raised to minus 27 square. That means delta E is of the order of, okay, it is of the order of, right, it's not equal to, it is of the order of this thing. 10 raised to minus 27 multiplied by 10 raised to minus 10. That is minus 37 is the answer. Option B. Okay, it is 10 raised to minus 10 plus 27. That is 10 raised to minus 37. A particle of mass m and charge q is placed at rest in uniform electric field E. So electric field is uniform, not changing, and then released. Then the kinetic energy attained by particle after moving a distance y is. So see, there is a particle, it's in uniform electric field. So electric field is constant. Okay, this is electric field, it's directed like this. So these are electric field lines shown to drawn to show uniform electric field. So they are equidistant. That means lines are equally spaced. So that means the electric field is uniform, and they are directed in same direction. Okay, so now you keep a charge here. So what will happen? Charge gets pushed by the electric field in this direction. Okay, so there is force on this charge due to the electric field, right? force is equal to Q into E, because E is equal to F upon Q, force is equal to Q into E. Okay, and now it moves through some distance y. It moves through this some distance y. So there is some work done. Work done is equal to force into displacement, because force is constant. Okay, uniform electric field is uniform, so it is equal to F into y. Okay, so it is Q into E multiplied by y, and then this work done gets stored as kinetic energy of the particle, right? This particle was at rest, it is pushed by electric field. Okay, so it gains some energy, kinetic energy, so it is equal to work done by the electric field on the particle. Okay, so this is the answer. QEY is the answer. Toy car with charge Q moves on a frictionless horizontal plane surface under the influence of uniform electric field. So there is a car which has charge Q. It moves on a horizontal surface under uniform electric field E. Due to the force QE, its velocity increases from 0 to 6 meters per second in 1 second duration. Okay, so velocity increases from 0 to 6 in 1 second. At that instant, the direction of field is reversed. Okay, so for 1 second, electric field is directed like this. So it moves, let's suppose, from here to here. Okay, right? This is for 1 second. So this is electric field, and this is the car. Moves from here to here in 1 second. This is toy car. Then when the car is at this position, okay, so car has charge Q. When it is at this position, the field is reversed. This is given. Field gets reversed. Okay. At that instant, the direction of electric field is reversed. The car continues to move for 2 more seconds. It continues. Yeah. Let me explain it once again. So you have this car. Okay. You have a toy car which is kept in uniform electric field, and this car has got charge Q. Okay, the car has got charge Q on it. So it is just placed there, right? It is just placed. So now, due to this electric field, because electric field will exert some force, car will move from this point to this point. Okay, it moves in 1 second, and it gains this much speed, right, from 0 to 6 meters per second. Now when it reaches this point in 1 second, the field is reversed. Okay, so now electric field acts in opposite direction. So now what will happen? So it keeps on moving for 2 more seconds, and the average velocity and average speed of the toy car between 0 to 3 seconds are respectively. This is the question. Okay, so now what will happen? The field is reversed. So now see, it has gained this much speed, this much velocity due to this electric field. Now if you exert opposite force, equal and opposite force, so its velocity will go from whatever it is to 0 in same amount of time, right? So it will go to some position. Actually it will travel same distance and stop. So this will happen in, okay, this has happened in 1 second. So this will again happen in 1 second, right? But it continues to move for 2 more seconds. This is given. So what will happen in next second? This is 2 seconds. Okay. So after 1 second, it keeps on moving till 2 more seconds. So 1 second plus 1 more second. So now it has stopped here, but electric field is acting in same direction. Okay. So it will move like this. It will move from here to here, then from here to here, and from this point it will move. So it will not take turn like this. It will move backwards from here to here. Again in 1 second, it will gain same velocity. Got it? In 1 second, it will gain same velocity. Okay. So now, question is average velocity and the average speed of toy car between 0 to 3 seconds. So to find out average velocity, we need to find out this displacement. Okay, so car moves from here to here. And to find out average speed, we have to find the distance. So the total distance is 3 times of this displacement. Okay, so let's do that. So how much is acceleration? Acceleration is, if we consider this thing, it goes from 0 to 6 meters per second in 1 second. So acceleration is v minus u divided by t, that is 6 minus 0 divided by 1, 6 meters per second square. Okay, so now we know how much would be this displacement. So it is s is equal to ut plus half at square, right? It starts with 0 velocity, so this thing is 0. Okay, this thing is 0, and this is equal to half of a, acceleration is 6 multiplied by t square, t is 1, so it is 3. Okay, so how much is velocity now? So why did I find only this much distance? Because it will come back at the same point after 3 seconds. Okay, so what is velocity? It is displacement divided by time. So it is s upon t. How much is that? 3 upon 3. So it is 1, right? 1 meter per second. But how much would be speed? So this is its displacement, but it has covered this much distance actually, from here to here, plus here to here, plus here to here. Okay, so it is 3 times. So speed is distance upon time, that is 3 times 3. So 9 upon 3. So it is 3 meters per second, right? So option B is the answer. An electron falls from rest through a vertical distance h in uniform and vertically upward directed electric field E. Okay, so electric field is directed like this, and you release this is an electric field, you release an electron and it falls like this. Okay, now the direction of electric field is now reversed, keeping its magnitude same. So now you have electric field like this, its magnitude is same. The proton is allowed to fall from rest in it through the same vertical distance h. Okay, so this is a proton, E plus, this is proton. So electron falls through distance h, okay, till here. Proton also falls to the same distance. The time of fall of electron in comparison to time of fall of proton is, option A is smaller, option B is 5 times greater, option C 10 times greater, option D equal. Tell me, this is quite recent, 2018. But acceleration of electron would be force divided by mass of electron, and acceleration of proton would be force upon mass of proton. Mass of electron is much smaller compared to mass of proton. Okay, and that's why acceleration of electron would be very large compared to acceleration of proton. And that's why what will happen, the electron will fall much faster compared to the proton. So time taken by electron will be much smaller. It's option A. So next question is, point charges plus 4q, minus q and plus 4q are kept on x-axis at point x equal to 0. Okay, so at x equal to 0 there is charge plus 4q. At x equal to a there is charge minus q, and x equal to 2a. Okay, you have plus 4q, right? Then only minus q is in stable equilibrium. All the charges are in stable equilibrium. All of charges are in unstable equilibrium. None of the charges is in equilibrium. So what will happen? Now let's suppose only these three charges are there and nothing else is there. So see, if we think about the force acting on plus 4q. So there is an attractive force due to minus q. There is a repulsive force due to plus 4q. Okay. Similarly, on this charge, there is an attractive force due to minus q. There is a repulsive force due to this plus 4q. Okay. So net force on this charge and this charge would be repulsive. So they will be pushed away. They will be pushed away, right? But what about this charge? So see, small q, it is pulled by this charge and it is pulled by this charge. And since these two charges are equal, okay, since these two charges are equal and the distance is also equal, okay, the distance is also equal from this charge. So what will happen? I mean, the net force on this charge is 0. Okay, the net force on this charge is 0. So that means this charge is in equilibrium. Got it? So none of the charges are in equilibrium is wrong. Okay. All charges are in equilibrium is also wrong. All of them are not in equilibrium. Okay. So all of them are neither in stable or unstable equilibrium. So option A is only correct. The charge minus q is in stable equilibrium. Let's see next question. A charge q is placed at a center of line joining two equal charges plus q. The system of three charges will be in equilibrium. Q is equal to. Okay. So charge small q is there and it is placed at the center of line joining two charges q and q. Okay. So then the system will be in equilibrium if q is equal. So now what you have to do is you have to find force on any other charge, because see, this charge will be in equilibrium, right? Because see, it is at same distance from this charge. Okay, it is at distance r. Let's suppose from this charge also it is at distance r, because we have kept it at the center. So this will be in equilibrium. There is no question about it. So now other two charges should also be in equilibrium. So force on this one should be equal to 0, net force, and force on this one should also be equal to 0. So let's calculate force on this one. So force on first charge. Okay, force on first charge. So it is k multiplied by q into q divided by r square, plus it is force on this charge due to this charge, plus k multiplied by k is 1 upon 4 pi epsilon naught q into q divided by how much is this distance? 2r, 2r square. Okay, and this net force should be equal to 0 for that to be in equilibrium. So then we can divide by q. Okay, sorry, then we can divide by k. It is q into q divided by r square plus q into capital Q upon 4r square is equal to 0. R square gets cancelled, q and q gets cancelled. Okay, so that means q plus q by 4 is equal to 0. That means Q is equal to minus Q by 4. Okay, so this charge should be of opposite nature and it is equal to minus Q by 4. So option A is the answer. Yes. Okay, so this is also a simple question. Next question. When air is replaced by a dielectric medium of constant K, the maximum force of attraction between two charges separated by a distance. Option A increases K times, remains unchanged, decreases K times, increases K times. So if air is replaced by some other medium, what will happen? So we have force in air is 1 upon 4 pi epsilon naught. Air is almost same as vacuum. Okay, multiplied by Q1 Q2 upon R square. And if some other medium, so for some other medium, it will be 1 upon 4 pi epsilon naught K. Okay, they have written it capital K. So multiplied by Q1 Q2 divided by R square. So it is inversely proportional to the dielectric constant, right? So that means if dielectric constant K is more, what will happen? The field will, the force will decrease K times. Okay, so answer is it decreases K times. It's inversely proportional, so it is option C. Let's see this one more question. Two positive ions, each carrying a charge small q, are separated by a distance d. If F is the force of repulsion between the ions, the number of electrons missing from each ion will be. Okay, this is the question. So F is the force. So you have two positive ions, right? So some electrons are removed from them, some electrons are removed from the atoms, so they become ions, right? So it can be 1 electron, 2 electron, 3 electrons. Okay, so atoms are neutral. When you remove electrons, they will become positively charged. So how many electrons are removed? So charge on this one is q, charge on this one is also q, distance between them is d. Okay, so if n electrons are removed, q will be equal to n times e, that much positive charge, right? So force can be written as 1 upon 4 pi epsilon naught, because there is 4 pi and epsilon naught in all options, multiplied by q square upon d square. Okay, because both of them have same charge. So this is equal to 1 upon, we can write q square equal to f multiplied by 4 pi epsilon naught into d square, right? And therefore q square is n square e square, because q is equal to ne. It is n square e square is equal to this thing, f multiplied by 4 pi epsilon naught d square. If you take n square on other side, sorry, you take e square on other side, we want to find out n, right? How many electrons are removed? So we'll take e square on other side. Okay, and then we'll get square root because we want n. So it will be square root of this thing. Okay, it's option C. 4 pi epsilon naught f multiplied by d square divided by e square.